So if I take y is equal to 3, this is a plane, right? So this is the plane right here. This blue plane, light blue plane, is y is equal to 3. And as you can see, it cuts, look at this trace right here. It cuts the surface and the intersection is going to be what? Well, the intersection is going to be nothing else but the function in one variable that we have evaluated, right? This right here is going to be the intersection between this surface right here and the plane y is equal to 3. So if I plot that, curve, that trace, this is what I was going to get, okay? So what is this? This is curve depending in what? Depending on one variable, right? Just depends on the variable x. So here I end up like this. So here both of them are positive. X-axis is positive, y-axis is positive. Obviously, this curve depends on x and produces values in terms of y, right? It's just, this curve is just two-dimensional, okay? So I end up talking about calculus 1, finding the slope of this curve at the point B is what? Finding a derivative in one variable, right? That exactly is what partial derivatives are. So here I can say find partial derivative of f with respect to x, right? When y is equal to 3. So that's equal to, because when y is equal to 3, this becomes function in one variable, d dx of negative x minus 2 squared plus 4. And this derivative is just negative 2x minus 2. Okay? So now we already know how to do all the calculus behind in order to find the derivative at this point, at the point B. Okay? So just find the derivative as we did, negative 2x minus 2, and then let's evaluate the derivative at the point B, at the point x is equal to 3. So that means partial f, partial x, evaluated when x is equal to 3 is negative 2x minus 2 when x is equal to 3. 3 minus 2 is 1, so negative 2. Okay? So that means that the slope of the tangent line of this two-dimensional curve, is negative 2. So let's check if that's correct. Okay. So here is the curve in 2 dimensions, right? Depends on x produces outputs in terms of y, because we took this light blue thing in the back, or gray, is the plane z is equal to 3. So here is the slope, here is the tangent line. This is the tangent line of this two-dimensional curve at the point B. Okay? And that exactly is what partial derivatives are, right? This is how it's going to look. On the other hand, if I take I take x being constant 2, and I express this function here for a constant x being x being constant. Yes. Yes. Any comments? Okay. Then this two-dimensional function becomes function in one depending on one variable. Function from two variables becomes function in one variable. So df dy is just negative 2y minus 3. Okay. And now I evaluate that at the point. I evaluate that at the point 3. Y is equal to 3. That means that the slope is equal to 0. So now check this. Partial f, partial y, and here taking y x is equal to 2 is equal to negative y minus 3, evaluated y is equal to 3, is equal to 0. Okay? That means that if I cut this surface here with the plane x is equal to 2, I should expect what? A curve depending on one variable such that at the point 3, because only depends on y, when y is equal to 3, I should get what? A horizontal tangent line. So let's go over all of this, right? Let's go over all of this in through the graph. So I'm going to take this out, okay? So this is the surface, okay? I'm taking y is equal to y is equal to 3. If I take y is equal to 3, what will that change? So if I take here 3, my bad, sorry, I haven't programmed this well. So I take the plane x is equal to 3. So this is x minus 1 is 3 minus 2 is 1, squared is 1, so negative 1 minus this plus 4. Again, the derivative, everything else is the same. Okay, sorry about that. So the plane is x is equal to 3. Otherwise, it wouldn't go through the point B, okay? So we can see the trace here. We can see the curve here. Moreover, I'm just gonna sketch that one. You see how the curve follows the intersection between the plane x is equal to 3 and the surface, okay? And only from this graph, it's obvious that the tangent line will be horizontal here, right? And we confirmed that by finding the derivative at y is equal to 3, and we got that the tangent line at B is horizontal. The tangent line is the slope is 0. Okay, so and we can generalize this. Okay, what if I find? Do I have to? This plane x is equal to 3 doesn't have to be exactly 3, right? It can be any plane such that it will intersect the surface, right? Similarly for the y plane. Similarly for the y plane, right? It can be any plane such that intersect the surface, right? So that will bring us to what? That will bring us to finding the derivative only in one variable. So whenever we talk about partial derivatives, we take any other variable, we treat any other variable just as a constant, and that's the whole story about partial derivatives. Very soon you will see in next week you will see, but even from this graph we don't have to wait until the next week. we can talk intuitively, we can talk about the maximum value of this function, right? Which is obvious, is right here, the absolute maximum. So the absolute maximum is going to happen at the point C, okay? Well, how are we going to find the point C, right? What do we, where the maximum happens from Cal 1? If there is a maximum or minimum, if there is a extreme value, then that value definitely happens where the tangent line is horizontal. That's not enough when a function is defined in two variables, right? Here you go. The tangent line is horizontal, right? But B is not maximum. Well, if in single variable calculus, I needed horizontal tangent line for a function defined in two variables, right? The maximum will happen where I have tangent plane. So horizontal tangent plane, right? So at the point C, the tangent plane will be horizontal. Okay, so that Z is equal to 4, right? So like this, because I have a maximum here, the tangent line, sorry, the tangent plane to the surface at the point where the surface reaches maximum or minimum is going to be horizontal. Well, in order to do that, what do I need, right? Plane is spanned by two vectors. So I don't need only it is not going to be enough that partial f, partial y is going to be I don't need only the partial derivative with respect to y to be 0. But because we talk about planes, I need also and partial f, partial x evaluated at the point to be 0. This is how we find, this is how we prove that AB is a critical number or critical point. Okay, so all of that we could see just from talking about partial derivatives. Okay, and of course we'll come back to this. First we have to practice. Today we'll practice partial derivatives, and then we'll do the chain rule, which is a little bit out there. Okay, maybe we'll start it today, we'll see. So let's do a lot of examples of partial derivatives. Okay, so let me find my examples now. That's a completely different story. Give me a second here, please, guys. And of course, I lost my examples, but I can always find them in my favorite book. And that's this one. I will just now I can stop playing with this, right? So this is my favorite book right here, which is just a collection of problems in mathematical analysis compiled by Demilovic, okay, from the Soviet Union, and there are some very famous names right here. Okay, and of course I have it in Serbo-Croatian from a very old country that doesn't exist anymore. But of course you can download this in English if you want. So I remember the page here. The page was 180, and that brings us to, well, let's do problem, I'll call it 1, but it's actually this one right here, 1801. Okay, so how many problems are there in this book? 3,000? I don't know. So 180, sorry. If you're interested, I'll give you this file. Okay, so find the partial derivatives, partial z partial x and partial z partial y, where the first problem is defined as z is equal to x cubed plus y cubed minus 3a is just a constant, xy. Okay, so first I'm looking for partial z partial x. Okay, so I treat every other variable as a constant. So in this case, this will be my constant. Negative 3a is a constant. Well, a stands for a constant, it's not a variable, and y is a constant. Then, once you do this, you switch back to Cal 1. So the derivative of x cubed is 3x squared. Derivative of a constant is 0. Derivative of x times a constant is the constant times the derivative of x. So that's a negative 3ay, because the derivative of x is simply 1. Now partial z, partial y. Okay, now I'm looking for the derivative with respect to y. That means every other variable, and here there are only 2 variables, is being treated as a constant. So that means x is going to be treated as a constant, right? So partial z partial y is equal to derivative of a constant, 0. Derivative of y cubed is 3y squared minus derivative of a constant times y is the constant, negative 3x times the derivative of y. Well, the derivative of y is 1, so this is my answer. Any questions? Okay, let's do the second one. F of xy, x minus y over x plus y. Partial f partial x, here I'm mixing the notation on purpose. Okay, it's equal to, well, here in order to evaluate this derivative, I have to use what? The quotient rule, treating y as any constant it is. So I have x plus y squared. By the quotient rule, we square the denominator right away, right? So all of a sudden, this is going to be step by step, and then I'm just going to stop writing this. Because I'm treating y as a constant, this becomes normal derivative dx of x minus y, because I'm treating y as a constant, times the denominator minus the numerator times the derivative with respect to x of the denominator, right? So I'm treating y as a constant. That means that the partial derivative becomes normal derivative. What we saw in the picture, the moment you take y or any other variable as a constant, the function becomes defined in a what? In a function of one variable. So that's why I can take d dx, okay? So derivative of derivative of x is 1, derivative of a constant is 0. So you have x plus y here, minus derivative of x is 1, derivative of y is 0. So minus x plus y over x plus y squared. And this is equal to 2y over x plus y squared. By the same logic, partial f partial y, square the denominator, okay? Now the derivative of the numerator with respect to y is -1, because I'm finding just the derivative of negative y, to power 1 is -1. Derivative of x, I'm finding the derivative with respect to y, so x is being treated as a constant. Derivative of constant is 0. Minus time, so -1 times the denominator, minus derivative of the denominator with respect to y. With respect to y, derivative of x is 0. Derivative of y with respect to y is 1. So that means minus x minus y. And then drop the parentheses, negative x minus y minus x plus y over x plus y squared. Partial f partial y is -2x over x plus y squared. Any questions? Okay, so let's do something interesting. Okay, so f of xy is equal to arc sine of square root. Oh, what is going on here? Okay, I need some feedback because the camera seems not to be working. So can you guys turn your mics and tell me what's going on?
I can still see everything.
And it's going well. It's flowing well. It's not a.
Well, to me, it's fine. Yeah.
Yeah, same.
Yeah,
Everything looks fine.
All right. Okay then.
Yeah.
So you have x squared minus y squared over x squared plus y squared. Okay. So just I'm going to remind you that the du of arc sine of u is equal to square root of 1 minus u squared, okay, times u prime. Okay, from Cal 2, where we learned about inverse trigonometric functions, or if any of you learned this in Cal 1, that means that your Cal 1 teacher was extremely ambitious. However, now I'm finding partial f, partial x. Okay, first of all, I follow this formula. Derivative of arc sine of u, whatever u is, what function u is, and this is obviously our u, right? It's equal to 1 over square root of 1 minus u squared. That's square root of x squared minus y squared over x squared plus y squared squared. That's 1 over square root of 1 minus u squared times u prime. But be careful now with respect to x. So square root of w prime is equal to 1 over 2 square root of w times w prime. Right? So that means 1 over 2 times square root of x squared minus y squared over x squared plus y squared times what? Times just this derivative here with respect to x. Times this derivative with respect to x, for which we're going to use the quotient rule, right? So that's x squared plus y squared squared. The derivative of the numerator is, with respect to x, is 2x times the denominator, x squared plus y squared. And this was, so I'm going to continue here, minus the derivative of the denominator with respect to x, which is 2x, times the numerator, x squared minus y squared. So this is the partial derivative of f with respect to x. Of course, you should be able to notice that things can be canceled, simplified here. So let's do that, and maybe I'll give you an answer for I'll give you the answer for the partial f partial y, and you can do it right at home. So how do we simplify this? This square root here squared, this square goes with the square root, and you get 1 minus x squared minus y squared over x squared plus y squared, okay, times square root of x squared plus y squared over 2 square root of x squared minus y squared. So what happened here, right? This is this part. Right, if you have 1 over a over b, that's b over a. That's what happened. Times, let's see here, 2x cubed plus 2xy squared minus 2x cubed plus 2xy squared. And here I have x squared plus y squared squared. Okay, so what can we cancel? 2x cubed and 2x cubed. Okay, this is 1 over square root of, now I bring this under common denominator, x squared plus y squared minus x squared minus y squared over x squared plus y squared times square root of x squared plus y squared over 2 square root of x squared minus y squared times 2 plus 2 is 4xy squared over x squared plus y squared squared. And for this expression, I use this identity also. So this ends up being square root of x squared plus y squared over square root of, I drop the parentheses here, x squared plus y squared minus x squared plus y squared times square root of x squared plus y squared over 2 square root of x squared minus y squared times 4xy squared over x squared plus y squared squared. Now let's cancel. Square root of a times square root of a over a squared is equal just to a over a squared, which is 1 over a. Square root of a times square root of a is just a divided by a squared is 1 over a. So I get, and 2 cancels with 4. So I get, 2xy squared over x squared and x squared cancels out. So I get square root of y squared, it's absolute value of y. Square root of y squared is absolute value of y, right? But here I don't have y squared, but y squared plus y squared is 2y squared, right? So I'm left with square root of 2. Okay. Times square root of x squared minus y squared times x squared plus y squared. And this is your answer. This is just the partial derivative with respect to x. Okay. Now, if you take y is positive, then you can cancel this y and this y, and so on and so on. You can simplify this expression even further. Any questions, guys? So look at this and tell me if you have some questions. Or you gave up on this, on the questions from this?
It's good.
All good? You're not worried at all?
No, not really. It's pretty similar to Cal 1, right? So
Yeah, it's very similar. It's based on Cal 1. So, okay, so then let's move on. Okay, so something similar. Show that example 2. Show that x partial z partial y plus y partial z. So this is x here, sorry. Partial z partial y is equal to 2, where z is equal to ln of x squared plus xy plus y squared. Okay. So here I have to find the partial with respect to x and y. So partial z, partial y. Okay, I don't know why I started with y, but doesn't matter. So ddU of ln of u is equal to u prime over u, right? So my u is this expression here, so x squared plus xy plus y squared. And then I'm looking for the partial with respect to y. That means the derivative of x squared is just 0. Derivative of x times y with respect to y is just x because it's written as a constant, plus y squared, derivative of y squared is 2y. And here, look at this, this is a very symmetric function, right? So you will get used to figuring that out very quickly and then just following through with the second partial derivative, x squared plus xy plus y squared. And then this is going to be y plus 2x, right? Look at the symmetry, right? Depending on what, with respect to what variable I'm finding the derivative. And then, of course, you can check this, right? Derivative of x squared with respect to x is 2x. Derivative of xy with respect to x is just y. Derivative of y squared with respect to x is 0. Okay, and now all you have to do is show this equality. So x partial z partial x plus y partial z partial y is equal to x times partial z partial x is y plus 2x over x squared plus xy plus y squared plus y times partial z partial y is x plus 2y x squared plus xy plus y squared. The denominator is the same, x squared plus xy plus y squared. Multiply this out, xy plus 2x squared plus xy, x times y is xy, plus 2y squared is equal to 2x squared plus xy plus xy is 2xy plus 2y squared over x squared plus xy plus y squared. It's obvious that if you factor 2 in the numerator, the second factor is going to be the same as the denominator, x squared plus xy plus y squared over x squared plus xy plus y squared, and that indeed is just 2 after we cancel this out. So we have shown that this is equal to this. Okay. Okay. So we have a second order partial derivatives, and here we'll have right, so find the second order partial derivative with respect to x, the second order partial derivative with respect to y, and both mixed partial derivatives, partial z, partial x, partial y, and partial z, second order, first with respect to x, then with respect to y. Okay, where z is equal to square root of 2xy plus y squared. Okay, so in order to get to here, I need to do what? I need to get to the first order partial derivative. So partial z, partial x is equal to 2 square root of xy, 2 times square root of 2xy plus y squared, right? Times the derivative of what's inside the root with respect to x. This guy doesn't depend on x, so its derivative is 0 with respect to x, and here I have just 2y. So that's y over square root of 2xy plus y squared. Partial z partial y is equal to, here I don't have a symmetry, right? So be careful not to fall in the trap. 2 times square root of 2xy plus y squared, derivative of this term with respect to y is 2x plus 2y, factor 2, and you get x plus y over square root of 2xy plus y squared. Okay, so the second order partial derivative with respect to x is partial with respect to x of the first order partial derivative with respect to x. So that's partial derivative with respect to x of what? Y over square root of 2xy plus y squared. This is a constant, so it goes outside. So basically we have to find the partial derivative with respect to x of 2xy plus y squared to power negative 1/2. And now you follow the Cal 1 rules. Y times negative 1/2 2xy plus y squared to power negative 3/2 times derivative of this term here with respect to x, and that's just 2y, right? Because only this one here depends on x. So you can write that second order partial derivative with respect to x twice is a negative, 2 and 2 cancels out, negative y squared over 2xy plus y squared to power 3/2. Okay. Second order partial derivative with respect to y twice is the partial order with respect to y of partial z partial y. That means of x plus y over square root of 2xy plus y squared. And for this one here, I have to use the quotient rule. So I square the denominator. That gives me 2xy plus y squared. Square the denominator. Derivative of the numerator with respect to x is 1. So I just get 1 times the denominator, square root of 2xy plus y squared, minus x plus y, the numerator, times the derivative of the denominator. Right? And the derivative of the denominator with respect to y is 2 square root of 2xy plus y squared times the derivative of what's inside with respect to y, and that's 2x plus 2y. Okay, let's simplify this. Second order partial derivative with respect to y twice is equal to, bring this under common denominator, and sorry, I'll cancel this right away. So there is no 2xy plus y squared. Multiply this by this and you get 2xy plus y squared minus x plus y squared. X plus y times x plus y is x plus y squared over 2xy plus y squared. Now this is to power 1, this is to power 1/2. When I multiply that, I get 2xy plus y half to power 3 over 2, right? This times this is equal to this. And then what do I have in the numerator? 2xy plus y squared minus x squared minus 2xy minus y squared. And this nicely cancels out. And the second order partial derivative with respect to y is negative x squared 2xy plus y squared to power 3 over 2. Okay, and then by the Clairaut's theorem, I know that the second order partial derivative, the mixed second order partial derivative, first with respect to y, then first with respect to x, then with respect to y, it has to be equal to the second order partial derivative, first with respect to y, then with respect to x. Okay, so by the Clairaut's theorem, I just have to evaluate one of this, and then the other one is going to be correct. So I'll evaluate one, and I'll leave the second one for you to confirm the Clairaut's theorem. So second order mixed derivative is equal to what? Partial y of partial z partial x. I told you to be careful about these two notations. This notation says first find the derivative with respect to x, then with respect to y. This one here says first find with respect to x, then find with respect to y. Okay, the positioning is different. Okay, so be careful. So here I have the partial order, the partial derivative with respect to y of partial z partial x is this one right here. So y over square root of 2xy plus y squared. And here I have to use quotient rule again, sorry about that. Square the denominator, 2xy plus y squared. Derivative of y with respect to y is just 1, so square times the denominator, 2xy plus y squared, minus numerator times derivative of the denominator with respect to y, and that's x plus y square root of 2xy plus y squared. Okay, so I just copied it from here. The derivative of this guy with respect to y, I've evaluated it here. I have to figure out ways how to be more effective when you do these problems, okay? Okay, so bring the numerator under common denominator. That common denominator is square root of 2xy plus y squared. That means I've multiplied this root by itself, which gives me 2xy plus y squared minus y times x is xy, y times y is negative y squared over 2xy plus y squared. Now in the denominator, I have 2xy plus y squared to power 3 over 2. Here I cancel these guys. And I simply have xy, 2xy minus xy is xy. This is why I like this collection of problems, because they usually gives aesthetics is very, in mathematics was very important. I'm not saying that it's not important elsewhere, but in Soviet Union was very important. So for mathematicians, also known as nerds elsewhere, this kind of symmetry is very interesting, right? So the second order partial derivative is, so only the numerator changed. Negative y squared with respect to y is negative x squared, and both mixed order partial derivatives are just mixed between x and y. So it's a cool story. It's an interesting, using a fancy word, narrative. Okay, any questions? And then I'm just going to give you a hint if you haven't seen already the video that's on YouTube on the chain rule. I'm just gonna give you a hint of what's going on. Okay, so chain rule, if I'm not mistaken, this section 14.1. Okay, so I have a function z defined in two variables. So f of x y is equal to e to power 3x plus 2y. Okay, where x is equal to cosine of t and y is equal to t squared. Okay, so you can see here that ultimately z depends on t. So the question here is, how much is dz dt? Now look at be careful of the notation. I'm looking for dz dt because z is defined only in terms of t. But prior to that is defined in terms of x and y. So in order to find dz dt, first I have to find the partial derivative with respect to x by the chain rule. Now x depends only on t, so notice the notation. X depends only on t, so the derivative is going to be written as dx dt. Okay, z depends on two variables, so partial z, partial x. X depends in one variable, dx dt. Okay, plus partial z, partial y, times y depends in one variable, dy dt. Okay, let's go now. Derivative of e to power u prime is e to power u times u prime, right? So this derivative with respect to x is e to power 3x plus 2y times the derivative of 3x plus 2y with respect to x. That's only 3. We should have no problem, Tanya. Okay, this is this derivative. Times dx dt. Dx dt is negative sine of t plus partial z partial y by the same logic, e to power 3x plus 2y times derivative with respect to y is just 2 times dy dt. Dy dt is just 2t. Okay, how I can simplify this expression? The only thing, so this here, factor out the common factor, 3x plus 2y, and you get negative 3 sine of t plus 2 times 2 is 4t. Okay. Usually, when x and y are defined in one variable, we plug them back in here. So the final answer is e 3 times cosine of t plus 2t squared times negative 3 sine of t plus 4t. Okay. There is an easier way how to look at this rule, right here. And that is just writing this tree, right? We said that z depends on x and y, and then x depends on t and y depends on t. X and y are defined in one variable. So then dz dt is going to be how to get to t. First, I have to go through x, partial z, partial x, y partial, because z depends on x and y. And then dx, x depends in one variable, dt, plus partial z, partial y, times, by the chain rule, dy dt. And I'm just going to give you a hint of what are we going to do next class, which is it tomorrow?
Yeah, it's tomorrow.
Okay, so these are not very difficult. Okay, so let's say that f of xy is equal to 2xy plus y squared. Easy problem, where x is equal to s times arctangent of p, and y is equal to e to power s times cosine of p. Okay, so now if the question is how much is partial f partial s, what do we have? F depends on x, y, then x depends on s and depends on p, and y depends on s and depends on p. Then how am I going to get from f to s? Partial f, partial x, times, now x depends in two variables, partial x, partial s, plus partial f, partial y, times partial y, again, y depends on two variable, partial s. So this is going to be equal to partial f, partial x, partial x, partial s, plus partial f, partial y, times partial y, partial s. That's just derivative of f with respect to s, this partial derivative. Hopefully you can notice what is going to happen when we will have, when you'll have to find the second order partial derivative when you have to apply the chain. Okay, but for that I will leave this part of the story for tomorrow, and then I will upload my prepared videos tonight. I guess if there are no questions, thank you very much for your attention, and